In this lesson, we explore how to write data to file and read data from file. In this section, we will discuss the basics of writing data to a text file. When accessing files in LabVIEW, there is a typical file I/O programming flow. First, you will open or create or replace the file. Second, you will read or write to the file. Third, you will close the file when finished. And finally, you will check if an error has occurred. These high-level file I/O nodes combine three steps: open, read or write, and close, all in one node. For example, executing the write delimited spreadsheet node will open a file, write data to the file, and close the file. In this example, the DACMX read node acquires multiple samples from 4 channels and outputs the data as a 2D DBL array. The write delimited spreadsheet string node opens or creates the file specified by the data log file path control, and then writes a header containing each channel name. The write delimited spreadsheet node inserts a tab delimiter between each column item, and inserts a new line character at the end of each row. Lastly, the write delimited string node closes the file. Next, the write delimited spreadsheet DBL node opens the same file, and then writes the 2D DBL array data to the file. Notice that append to file is set to true, which means this node will not overwrite the headers written by the previous write delimited spreadsheet node. Notice that the VI had to first transpose the 2D array to make each column represent a channel. Again, the write delimited spreadsheet node inserts a tab delimiter between each column element and a new line character at the end of each row. Lastly, the node closes the file. Use low-level file I/O nodes when you need to control each step. Low-level file I/O nodes provide individual nodes for each step. In the example VI, the first node opens an ASCII text file, then another node writes to that file repeatedly in a loop. Then the last node closes the file. As you can see, the write-to-text file node might be called hundreds of times, but the open file and close file nodes only happen one time. If you need to write or read multiple times to the same file, you should use low-level nodes for better performance. In contrast, if you use a high-level node inside a loop, it will open, modify, and close the file every time the loop executes, which will have worse performance. Reference numbers, or refnums, are temporary pointers to a resource such as a file, device, or object. Refnums serve as unique identifiers of that object. A refnum is created when the user opens or creates a file. In this example, the refnum is wired to each file I/O node and allows the write-to-text file node to know which file to write to, and allows the close file node to know which file to close. If you want to stream or continuously write numeric data to file, you should use the low-level file I/O nodes. A common example of this is streaming your acquired data to file. When writing numeric data to a text file, you must first convert the numeric data type to a string data type, because the write-to-text file node's text input is a string data type. One way to convert numeric data to a string is by using the numeric conversion nodes. This example converts the floating point numeric by using the number to fractional string node. The precision input specifies the number of digits after the decimal point in the output string, in this case, 3 digits after the decimal point. So you can see that the floating point data type has been converted to a string of 0.897. Let's look at how to convert a DBL data type into a string data type using the number to fractional string node. Notice as I change the precision input value, I can adjust how many digits after the decimal point appear in the resulting string. What if you have several items and data types to convert into a single resulting string? For example, a string that looks like this. You can use a single format into string node to perform this conversion. The format into string node requires some practice to use, but it is very useful for conversions into strings. So first, let's place a format into string node on the diagram. In this example, I have 3 items that I want to convert into a string: username, sample rate, and number of samples. So I'll resize the format into string node to show 3 inputs. Notice that by default, these inputs are a DBL data type. Next, I will define the expected data types for these inputs by creating a constant for the format string input. I can then place format specifiers or percent codes to define the data types of each input and how I want the resulting string to appear. So first, I'll type in a %s for a string input, then %f for a floating point input that will appear with a fractional format in the resulting string, then %d for a signed decimal integer. For more information on these and other format specifiers and percent codes, look at the help for this node. Now, notice that the input data types have changed. Now, I will wire my inputs. And now, I will create my resulting string indicator. Let's run the VI. As you can see, the %s has been replaced by the string input, the %f has been replaced by the DBL input and shows the DBL in a fractional format with a decimal point, and the %d has been replaced by the signed integer input. I can also type constant strings around my format specifiers or percent codes in my format string input. Now, when I run the VI, the resulting string looks like this. There is additional syntax available for my format specifiers. For example, I can add a .3 to my %f to specify the precision or number of digits after the decimal point for my floating point conversion into string. This example shows how to stream one channel, one sample data in a loop. First, we create a file. Then, we write a header to the file by writing a descriptive name for the data and an end-of-line character. Then, in the loop, we acquire one sample each iteration and use the format into string node to convert the numeric into a string and add an end-of-line character, and then write this to the text file. This happens in every loop iteration until the user clicks the stop button. Lastly, after we exit the loop, we close the file. In this section, we will learn how to write multi-channel data to a text file. This example shows how to stream n-channel one-sample data in a loop. First, we create a file. Then, this string array contains the channel names. The array to spreadsheet string node converts the array into a single string that contains each string in the array separated by a tab and adds an end-of-line character at the end. Then we write the string to file to create the header. Then, in every loop iteration, we acquire a 1D array containing one sample from each channel and use the array to spreadsheet string node to convert the numeric array into a single string that contains each numeric separated by a tab with an end-of-line character at the end of the string, and then write this to the text file. This happens in every loop iteration until the user clicks the stop button. Lastly, after we exit the loop, we close the file. This example shows how to stream n channels, n samples data in a loop. First, we create a file. Then, the string array specifies the column names for the file. The array to spreadsheet string node converts the array into a single string that contains each string in the array separated by a tab and adds an end-of-line character at the end. Then we write this string to file to create the header for the first line in the file. Then, in every loop iteration, we acquire a 2D array containing multiple samples from each channel and use the transpose 2D array node so that each channel's data is represented by a column instead of a row, and then use the array to spreadsheet string node to convert the 2D numeric array into a single string that contains each column item separated by a tab character and each row separated by an end-of-line character. Then we write this string to text file. This happens in every loop iteration until the user clicks the stop button. Lastly, after we exit the loop, we close the file. In this section, we will learn how to programmatically create file and folder paths. The first method of creating a file or folder path is to specify a hard-coded absolute file path, as shown in this file path constant here. An absolute file path describes the location of a file or folder starting from the top level of the file system, such as C drive. Another way to create a file path is to use the File Dialog node to launch a file dialog asking the user to choose a file themselves. You can also create a relative path. A relative path describes the location of a file or folder relative to another location in the file system. The getComponentDirectory node returns the path to the directory containing the project, that is, the .lv project file. This example uses this node and the buildPath node to create a relative path to a mydata.txt file in the same folder as the project. The getSystemDirectory node returns the system directory specified by its type input. This example uses this node and the buildPath node to create a path to a mydata.txt file in the user's desktop directory on their computer. For a list of available system directories, refer to the LabVIEW NXG help. Using relative paths makes your code more portable from computer to computer than absolute paths. This common real-world example programmatically creates a file name based on the current date and time. The getCurrentTime node returns the current timestamp. The formatDateAndTime string node then converts the timestamp into a string based on its time format string input. In this example, the time format string converts the timestamp into a string starting with the year, then month, day, an underscore character, hour, minute, second, another underscore character, and then mydata.txt. This example then uses the getComponentDirectory and buildPath nodes to make this into a relative file path in the same directory as the project file. In this section, we will show how to read and analyze data in a text file. Let's say you have already collected and stored all your data in a text file. Now, you want to analyze and process that data. This type of processing is called offline processing because you have already finished acquiring all the data. A delimited text file is a common human-readable format. Many text editors, spreadsheet editors, and analysis tools can read and process a delimited text file, so you can use your preferred tool for viewing and analyzing the data in this type of file. For example, you could view, analyze, and process a delimited text file using Microsoft Excel. You could also use LabVIEW to easily read data contained in a delimited text file and use built-in analysis nodes and your own custom logic to process the data. To do this, use a readDelimited spreadsheet node configured to read string data, and indexArray node to extract the first row of the file, which contains the header. Then, use another readDelimited spreadsheet node configured to read DBL data and array subset node to extract the data from the second line to the last line as a 2D numeric array. You can then process the 2D numeric array, for example, transposing it, searching it, running algorithms on it, and more. In this section, we will quickly compare file formats. There are three common file types that you might work with in LabVIEW NXG: text files, TDMS files, and binary files. Text files are the easiest format to use and share, as many applications, such as Notepad and Microsoft Excel, can read from or write to a text file. Data is represented in strings in text files. TDMS is a binary file format created by National Instruments that is optimized for saving measurement data to file. You can use TDMS files to organize data and store information about your data. You can also use TDMS files to write and read data at high speeds. You can also use an add-in to view TDMS files in Microsoft Excel. Binary is a file format that you can use when you want to write to or read from a binary file with a specific binary format. Explore this table to compare text, binary, and TDMS files. You've completed this module. Here is a summary of what you've learned.